In the today's class, we will study the qualitative study of this parallel resonant circuit. Okay, what is parallel resonant circuit, and how does the current in the circuit behaves with respect to the frequency of AC? That we will study. So, parallel resonant circuit is the AC circuit containing inductor and capacitor in parallel. Okay, that is called as parallel resonance circuit. An AC circuit containing an inductor and a resistor in series, and this combination is connected in parallel with a capacitor, is called as parallel resonance circuit. Okay, in the parallel resonance circuit, we will have a resistor and an inductor. They are connected in series in one branch, and this combination is connected with the capacitor in parallel. Okay, and this combination is finally connected to the external AC supply. Okay, so this is a AC circuit containing a resistor and inductor in series, and this series combination is connected to the capacitor in parallel. Okay, and this entire combination is then connected to the external AC, and we represent the AC voltage in terms of J operator method. And here voltage of AC applied is V equal to V naught into e to the power j omega t, where V naught is the peak voltage, J is the complex number of operator, complex operator, omega is angular frequency of AC, T is the instantaneous time. Here C is the capacitance of the capacitor, L is inductance of the inductor, and R is the resistance of the resistor. Okay, so this is also called as RLC parallel circuit. Okay, so parallel RLC circuit antanu idannu karitare. Series RLC circuit already we have studied. Parallel RLC circuit is looks like this particular circuit, and this is called as parallel resonant circuit. Okay, so this type of circuit is called as parallel resonance circuit. What it consists of? It consists of, this is a AC circuit consisting of resistor and inductor connected in series, and this series combination is connected to the capacitor in parallel. That is called as parallel resonance circuit. Okay, otherwise parallel RLC circuit. So how does the current varies in this circuit? We will see, and we are not going to derive the expression for current. It's a qualitative study, not in detail. Okay, so in parallel resonance circuit, what happens? The impedance of the circuit is given by this particular expression. So we are not going to derive this. You just remember, we are going to discuss this parallel resonance circuit qualitatively, not so important corresponding to your syllabus. Okay, so Z is given by square root of R square plus omega square L square whole divided by 1 minus omega square LC the whole square plus omega square C square R square. You remember this expression, that's all, but not necessary to discuss in detail. This is the impedance of the circuit corresponding to the parallel resonance circuit. In case of parallel resonance circuit, the condition of resonance is defined using the power factor of the circuit. Okay, so series resonance circuit alli ಏನು ಮಾಡ್ತೇವೆ, the condition of for resonance is given by omega L is equal to 1 by omega C. But here we define the condition for resonance in terms of the power factor of the circuit. What do you mean by power factor? Basically, the power factor is defined as cos of pi, where pi is the phase difference between alternating voltage and current. Suppose pi is the phase difference between voltage and current in the phasor diagram. Okay, then cos pi is called as power factor of the circuit. Okay, how do you define power factor of the circuit in AC circuit? Power factor is defined as cosine of the phase angle between voltage and current. Cos pi is called as power factor. If the impedance of the circuit is purely resistive, then obviously the voltage and current will be in phase and power factor becomes unity. Okay, let us take the case where impedance of the circuit is purely resistive. Okay, so no inductance or no capacitor is contributing for the impedance, only resistor is contributing for the impedance. Then what happens? Voltage and current will be in phase. We already know that in a AC circuit containing the pure resistor, the voltage and current will be in phase. There is no phase difference. Pi will be equal to 0. So they will be in phase. Voltage and current will be in phase. Therefore, the phase difference between voltage and current will be 0 if impedance is purely resistive, if impedance is equal to R. So if pi is 0, then what will happen to the value of cos pi? Cos pi will become 1. If pi is 0, then cos of 0 is 1. So when impedance of the circuit becomes equal to R, if Z equal to R, then pi will become 0 and cos pi will become 1. That means power factor becomes unity. Power factor will be equal to 1. And that is actually the condition for resonance in parallel resonant circuit. When power factor of the circuit becomes unity, the parallel resonant circuit is said to be in resonance. Okay. So in series resonance circuit, we have seen that the condition for resonance is given by omega L equal to 1 by omega C. And in that case also, the impedance will be purely resistive. Okay. Allu kuda enagtade, the power factor will be unity. Okay. So here purely the resonance is defined by the condition that the power factor of the circuit should be equal to unity. Okay, that is the condition for resonance in parallel resonance circuit. Just to remember, what is the impedance of the circuit? It is depending on R, L, and C, and then power factor of the circuit decides the resonance. If power factor of the circuit equal to 1, then the parallel resonance circuit is said to be at resonance. At resonance, what will happen? In parallel resonance circuit, it is reverse. At resonance, the impedance of the circuit becomes maximum and current becomes minimum. You remember this. In series resonance circuit, what was observed? At resonance, current becomes maximum. But in parallel resonance circuit, impedance becomes maximum and current becomes minimum. Therefore, this circuit is also known as anti-parallel circuit. Okay. The resonance curve for parallel resonance circuit is shown by this particular graph. And just you remember, this impedance becomes maximum. This is the curve for impedance. The current curve is reverse. Exactly, the graph is observed to be reverse in series resonance circuit. Okay, impedance increases and impedance becomes maximum at resonance, and current becomes minimum at resonance. In series resonance circuit, what we have observed? We have observed current becomes maximum at resonance and impedance becomes minimum. Therefore, in parallel resonance circuit, impedance becomes maximum at resonance and current becomes minimum. And this is the graph which shows the variation of impedance and variation of current with frequency. And this is called as resonant frequency. The frequency at which the current becomes minimum is called as a resonant frequency of parallel resonant circuit. Series resonant circuit alladre enaಗ್ತದೆ, the frequency at which the current becomes maximum is called as resonant frequency in case of series resonant circuit. But in case of parallel resonant circuit, the current becomes minimum at resonant frequency. It is exactly reverse. Okay. The resonant angular frequency of the signal and resonant frequency of the parallel resonant circuit is given by these two expressions. And here the expression for omega r is given by square root of 1 by LC minus r square by L square. And here the resonant frequency in parallel resonant circuit is given by Fr is equal to 1 by 2 pi into square root of 1 by LC minus r square by L square. And we are not going to derive this. You just remember, this is the expression for resonant frequency, because we are having only qualitative study of resonant, this parallel resonant circuit. And look at the expression here. Compared to the series resonant circuit, an extra term is added here. Okay, extra term, that is minus r square by L square, is added here. For series resonant circuit, the resonant frequency is given by Fr is equal to 1 by 2 pi into square root of 1 by LC. That's all. But in parallel resonant circuit, an extra term is there. Therefore, this resonant frequency also depends on resistance, inductor, and inductance and capacitance. All three components are going to decide the resonant frequency of parallel resonant circuit. Here omega R and Fr. Omega R is the angular resonant frequency. Fr is the simply resonant frequency. It is an angular frequency. This is the frequency of AC at which current becomes minimum. At this frequency, the impedance of the circuit becomes maximum and current falls to its minimum value. Okay, at this particular frequency, what will happen? The current reduces to the minimum value. Okay, current takes the minimum value and impedance takes the maximum value. That frequency is called as resonant frequency of parallel resonant circuit. Therefore, this circuit is also known as rejector circuit. Since current becomes minimum, it is also called as rejector circuit. It rejects the signal of certain frequency range above the resonant frequency. Therefore, parallel resonant circuit is called as rejector circuit. Series resonant circuit is called as acceptor circuit. Okay, it's a selective circuit. Yaudu series resonant circuit is called as selective circuit and it is called as the rejector circuit. Next, also when resistance is negligible, the resonant frequency and impedance of the circuit at resonance is nearly given by same as the series resonant circuit. So if R is very small, if resistance of the circuit is very small, then Fr will be equal to 1 by 2 pi into square root of LC and maximum impedance will be equal to L by CR. So this expression you remember, the impedance becomes maximum at resonance. That's why we have to take the maximum value of impedance at resonance and that is equal to L divided by CR. That is the value of maximum impedance of the circuit and that is observed at the resonance. Okay. Here Z max is having the dimensions of resistance and hence the impedance is purely resistive at resonance. Okay. So here Z max is having the dimensions of resistance and hence impedance is purely resistive at resonance. The current and voltage will be in phase with each other at resonance. Okay. Resonance at resonance, this is the frequency. Okay, this is the frequency at which resonance occurs. And at resonance, impedance becomes maximum, and that is having the value L by CR. And what is the phase difference between voltage and current? That is 0. Or the current and voltage will be in phase with each other at resonance. Similar to series resonant circuit, quality factor, sharpness of resonance, and bandwidth of the circuit can be defined. And expression for quality factor is same, that is omega R L divided by R, same expression. Or you can write quality factor equal to 1 by omega R into CR. There is no difference, exactly that is same. So no need to discuss again. Then bandwidth is also defined by F2 minus F1, where F2 and F1 are the half power frequencies. Okay, F2 is upper half power frequency, F1 is lower half power frequency. Okay. And this is the frequency at which the impedance of the circuit falls to 1 by root 2 times the maximum value. Remember, F2 and F1 are defined in terms of the impedance, because in the parallel resonant circuit, impedance becomes maximum at resonance and impedance falls to 1 by square root of 2 times the maximum value of impedance at the frequency equal to F2 and F1. And bandwidth is defined using this particular